sequence or initial binary sequence, we can identify the binomial sequence decomposition of the whole sequence. We will end when we reach all zeros and all zeros sequence. Our output will be the decomposition of the whole sequence. And we can see a characteristic of this algorithm is that mostly it reduces the length of the studied sequence by a few bits in each step. This is interesting because it means we can improve this its performance with two facts. The first one is that we only need the maximum binomial sequence. So instead of doing all the decomposition, we can find just the maximum. And the next fact we are going to use is that the binomial sequence are symmetric. They have a period. We can see that the first half and the second half both match. And we are going to use it to improve the basic algorithms. The result is the folding BSD algorithm, which also takes a binary sequence as its input. And what it's going to do is from the binary sequence, we are going to take the first half and the second half. We're going to add both. And if the result isn't all zeros, we will update the maximum binomial sequence and keep going with the addition. If the result is all zeros, we will just keep one of the two halves and continue with our algorithm. If we take the same binary sequence of our previous example, we can see how it works. We take the first half and the second half. We did its addition, and the result isn't all zeros. So we update our maximum binomial sequence and keep going with the addition of both. We then take the first half and the second half, and then our result is all zeros. So we just keep going with one of the half. We take one of the half and we repeat again until we reach the all zeros sequence. We will get then the maximum binomial sequences, which we can see match the previous one. But with this algorithm, we can see how the length of the sequence we are processing in every step is finally reduced by half in every step, which didn't happen with the basic BSD algorithm, which only reduced the length in a few bits. So as a conclusion, we could see the importance, the relevance of the binomial decomposition as a powerful tool to extract information from given sequences. We have seen two different algorithms to compute the binomial decomposition. The first one computes all the binary decomposition. The second one only search for the maximum binomial sequences, but with better performance. Both algorithms improves the performance of the traditional Berlekamp-Massey algorithm, which is the de facto algorithm for computing linear complexity of a binary sequences. And we can see how the periodic structure of the binomial sequences can be used to improve our algorithm. And maybe there is further work in this topic, because maybe we can improve, we think we can improve the performance of the folding BSD algorithm. And that will be all. Thank you for attention, and sorry for the sound and audio problems. Thank you.
Thank you very much, Martin. And I will ask the audience if there is any question. Just checking, but it seems that there is no question. So I would like to ask you if you can give us some more details on how much the performance has increased with your approach, so the folding BSD algorithm, with respect to the
Yeah, well, the Berlekamp-Massey algorithm, which is like the classic algorithm to do this kind of operations, mostly needs 2 times the length of the sequence to study it. So if we are talking about a sequence of length n, we will need the double of n to use this algorithm. With the basic BSD algorithm, we just need the sequence. We just need n bits of the sequence to apply it. And in every step, we are going to do like n additions because we are adding up two sequences of the same length. This is like a linear complexity of this algorithm. With the folding BSD algorithm, we are reducing the length of the additions and of the sequence by half. So we got a logarithm complexity of the algorithm. Well, that's
Okay.
quite impressive.
Okay.
If we think Thank you.
Okay, thank you. I don't know if there is no question still from the audience. We can move on to the third paper that is construction of the regular dodecahedron with a mathematic, and
Marcelo is here.
Is Marcela here?
With the interpreter.
Okay, but since I don't see their names here, I don't know. Okay, yeah. Sorry for this, but it's difficult to keep up with only the icons. Okay, so Marcela, the stage is yours. You have the microphone muted. And
interpreter, I'm waiting for Marcela. Can you hear me?
Yes, now we can.
Nice,
Yeah,
nice.
perfect.
Marcela, es tu turno. Marcela, is your turn.
Activo el micrófono. Disculpen.
Okay.
Ya. Ah, no había activado el micrófono, disculpen, por favor.
No problem.
She hadn't activated the microphone. She's apologizing now. Debes empezar. You should start.
Ya. Disculpen. Adiós. ¿Pueden visualizar?
Can
Sí, se
you
visualiza.
see it?
Yes, we can.
Ya, muy bien. Buenos días, estimado público y organizadores de la Conferencia Internacional sobre Ciencia Computacional y sus aplicaciones. Mi traductor, el señor Luis Vázquez Coronel, va a traducir simultáneamente lo que yo les voy a hablar.
Good morning, dear audience and organizers of this international conference about the science of programming and its applications. Mr. Luis Vázquez is going to be my interpreter.
El trabajo de investigación titulado Construcción del dodecahedro regular con el Mathematic ha sido trabajado por Ricardo Vélez Moro León, Jorge Luis Jr. Jiménez Gómez y quienes habla Felicita Marcela Velázquez Fernández.
This research titled Construction of the Regular Dodecahedron with Mathematics has been worked by Ricardo Vélez Moro León, Jorge Luis Jr. Jiménez Gómez, and the presenter Felicita Marcela Velázquez Fernández.
La exuberante geometría de los poliedros regulares atribuye a la naturaleza de su geometría, estética, simbolía, mística y cósmica ha fascinado a todas las civilizaciones a lo largo de la historia y ha sido observada en la naturaleza y en la construcción hechas por el hombre.
The exuberant geometry of the regular polyhedrons attributed to the nature of its geometry, aesthetics, symbology, mystics, and its cosmology have fascinated all the civilization through history, and it has been appreciated in nature and in humankind's work.
Su estudio se ha realizado a través del razonamiento, construcción y programación y visualización usando el software Mathematic 11.2.
Its study has been fulfilled through reasoning, construction, programming, and visualization using Mathematic 11.2 software.
La primera interrogante que surge, ¿podemos construir un dodecaedro partiendo de un pentágono regular inscrito en una circunferencia de radio 1?
The first question that comes up is, can we construct a dodecahedron based on a regular pentagon described in circumference of radius 1?
Se sabe que el sólido platónico de 12 caras tiene 20 vértices. Para responder a esta pregunta se partió de una circunferencia de radio 1 que descansa en el plano XY y cuyo centro es el 0,0,0. Conociendo el ángulo central podemos generar los vértices del pentágono regular que llamaremos base.
It is known that the platonic solid of 12 faces has 20 apexes. To give it an answer, we based on a circumference of radius 1 that lies on the xy plane and whose center is 0,0,0. Knowing the central angle, we can generate the apexes of the regular pentagon we will call base.
Para el siguiente pentágono regular al que llamaremos cerca de la base, se observó que la distancia entre dos puntos no consecutivos pero próximos es la medida del lado de dicho pentágono, el cual nos permite calcular el radio y la circunferencia que le inscribe, cuyo valor es el número áureo aproximadamente 1.618. La distancia entre los pentágonos regular base y cerca de la base es 1.
About the following regular pentagon we call near the base, it was observed that the distance between two non-consecutive but close points is the measure of the side of that pentagon, which lets us calculate the radius of the circumference that describes it, whose value is the golden ratio, approximately 1.618. The distance between the base regular pentagon and the near the base pentagon is 1.
Posteriormente se construyó el pentágono regular llamado cerca de la base, inscrito en una circunferencia cuyo radio es el número áureo aproximadamente 1.618 y cuyos vértices han rotado 36 grados respecto a los dos primeros pentágonos regulares y se encuentra a una altura aproximada de 1.700.
Afterwards, we constructed the regular pentagon called near the base, described in circumference, whose radius is the golden ratio, approximately 1.618, and whose apexes have rotated to 36 degrees in relation to the two first regular pentagons, and it is found at an approximate height of 1.700.
Y por último se construyó el pentágono regular llamado techo, inscrito en una circunferencia de radio 1 y que se encuentra respecto al plano XY aproximadamente a 2.700. Los vértices de este polígono han rotado 36 grados respecto a los dos primeros polígonos regulares.
At the end, it is constructed the regular pentagon called top, inscribed in a circumference of radius 1, and it is located in relation to the XY plane, approximately at 2.700. The apexes of this polygon have rotated 36 degrees in relation to the two first regular polygons.
Para la construcción y la visualización del dodecaedro, partiendo de un pentágono inscrito de radio 1, se ha usado los comandos de Mathematic 11.2 para Metriplot 3D, Delete, Table, Graphic 3D, Norm y Show, como han podido visualizar en las diapositivas.
For the construction and visualization of the dodecahedron based on a scribed pentagon of radius 1, we use the commands Mathematic 11.2, Parametric Plot 3D, Delete, Table, Graphics 3D, Norm, and Show, as you could see in the slides.
Posteriormente se procedió a trasladar los vértices del dodecaedro y que el centro del sólido platónico coincida con el centro de coordenadas del sistema.
Then we translated the apexes of the dodecahedron and made the center of the platonic solid coincide with the center of the coordinates of the system.
Surge una nueva interrogante. ¿Podemos construir el dodecaedro inscrito en una esfera de centro 0,0,0 y de radio r? Para ello se divide todos los puntos que representan los vértices del dodecaedro trasladado entre la distancia del centro del dodecaedro encontrado a uno de sus vértices. En nuestro caso, aproximadamente 1.680, logrando generar un dodecaedro inscrito en una esfera de radio 1. Se procedió a programar usando los comandos module, chot, conve, holmex y graphic 3D para generar un dodecaedro inscrito en una esfera de radio R.
But a new question comes out. Can we generate a dodecahedron scribed in sphere of center 0, 0, 0, and of radius r? For that, we have to divide all the points that represent the apexes of the translated dodecahedron by the distance of the center of the dodecahedron found to one its apexes. In our case, approximately 1.680, getting to generate a dodecahedron scribed in a sphere of radius 1. We decided to program using the commands modeled, showed, convex Hall meshed, and graphics 3D to generate a dodecahedron scribed in a sphere of radius r.
Y por último podemos generar, surge una nueva interrogante, podemos generar el dodecaedro a partir de una esfera inscrita en él y de centro 0,0 y de radio r. Para ello hallamos un punto de tangencia de la esfera con el dodecaedro trasladado. Haciendo el análisis respectivo, el punto de tangencia coincide con el centroide de alguna de las caras del dodecaedro trasladado. La distancia del centro del dodecaedro trasladado a un punto de tangencia es aproximadamente 1.320. Luego se procedió a dividir a cada uno de los puntos de los vértices del dodecaedro trasladado por el radio hallado. Se procedió a programar usando los comandos module, show, convex, holmex y graphic 3D para generar un dodecaedro que inscribe a una esfera de radio R.
Finally, there's one more question. Can we generate a dodecahedron based on a sphere scribed in itself with center 0, 0, 0, and radius r? For that, we find a point of tangency of the sphere with the translated dodecahedron. Analyzing the point of tangency coincides with the centroid of some of the faces of the translated dodecahedron. The distance of the center of the translated dodecahedron to the point of tangency it's approximately 1.320. Then we divide the points of the apexes of the translated dodecahedron by the found radius. We programmed using the commands modeled, showed, convex Hall meshed, and graphics 3D to generate a dodecahedron that describes a sphere of radius r.
Las conclusiones. El dodecaedro se construye a partir de pentágonos regulares paralelos. La relación de los radios de la esfera circunscrita e inscrita al dodecaedro trasladado es aproximadamente 1.273. Se sugiere extender la investigación y crear paquetes de programación de todos los sólidos platónicos, luego aplicarlos a diseños de la arquitectura poliédrica de diferentes objetos artificiales u organismos existentes de la naturaleza, como son la molécula de hidrato de metano, el polen, los arquetipos de estructuras esqueléticas de los radiolos, etc. Muchas gracias.
Conclusions. The dodecahedron is constructed based on the parallel regular pentagons. The relation of the radiuses of the spheres, the circumscribed one and described one, of the translated dodecahedron, it's approximately 1.273. We suggest extending the research and creating packages of all the platonic solids, and then apply them to the design of the polyhedral architecture of different artificial items or existing natural organisms, such as methane hydrate, the pollen, archetype of skeletal structures of radiolarian organism. Thank you very much.
Okay, thank you very much for your presentation. And again, I ask the audience if there are any questions. It doesn't seem so. And well, I have a general question. You reported the construction of the dodecahedron through particular commands in Mathematica, which is a particular environment for both building and visualizing these geometrical shapes. And the question is this one. Are you able to define a more general algorithm, a high-level algorithm for creating the dodecahedron outside the Mathematica environment?
Marcela, te dicen que tú has postulado la construcción de un dodecaedro a partir de unas cifras que incluyen 0. Si tú podrías utilizar un algoritmo de mayor nivel fuera de las matemáticas para sustentar esa idea.
Fuera del programa de Mathematics, me están preguntando. Claro,
Yeah.
sí, lo que pasa es que, bueno, en realidad no, lo que estamos aquí haciendo es hacer la construcción a partir de una figura regular, ¿no? Y,
Okay.
y obtener los vértices en este caso, de dodecaedro, y de ahí a partir de esos vértices, en ese caso, bajo esa estructura, poder generar cualquier tipo de dodecaedro, bajo un radio cualquiera de una esfera, ya sea inscrita o circunscrita al mismo dodecaedro. Y
Okay,
sí se
just a
podría
minute.
llevar a otro tipo de lenguaje de programación.
Okay, just a minute. What they're doing, it's using a geometrical shape, okay, using the apexes. But if it's a bar, to construct a different, okay, way, so they can do it.
Okay, yeah, because in this way the solution is much more appealing also for people that are working in different areas, like I don't know, computer graphics or something like this. Okay, it's
Sí,
clear.
te dicen que, Marcela, que lo que tú has hecho está más ligado a una esfera o a un lado de la construcción de gráficos para gente que se dedica a ese tipo de diseños.
Sí, pero el objetivo es, o sea, la cuestión que nosotros queremos sería generar, en ese caso, los vértices, ¿no? Entonces, al conocer ya los vértices de un dodecaedro, ¿no es cierto? Partiendo, en ese caso, de una estructura básica, podríamos ya ampliar los estudios para hacer, por ejemplo, modelamientos, en ese caso, para situaciones que se refieren a organismos biológicos.
Okay. Since they work in apexes, then they can construct based on apexes many other forms or ways to do it.
Okay, thank you very much. I see. Okay, that's perfect. I ask again if some of the authors of the first paper have arrived, but it seems not. Okay, so we can close also this session. Thank you to all the presenters and thank you for participating in this session.
Grazie Davide.
Prego, ciao, grazie.
Ciao Davide.
Ciao.
Live streaming is on.
Hi. Hi, I'm Sarah, the GT
Sorry?
moderator. Your microphone is
Yes,
closed.
I'm Luisa.
Sorry, what?
Luisa,
Luisa?
can you hear me?
Yes, yes.
Okay, all right.
Okay, you're the first presenter.
No, I believe I'm the second one. The first,
Okay,
I'm the two in both papers,
okay.
but I should be the second one. The first one will be Mahamar,
Okay.
all right?
Yes, thanks. We are
Okay.
on a break until
Yes, I know,
1:30.
understand.
Okay.
Okay, thank you.
So
So
see
no
you
problem.
in some minutes.
Sorry?
See you in some minutes.
Yes, okay, no problem. I'll be waiting. Thank you.
You're welcome. Luisa, we are still live on YouTube,
Okay,
in live streaming.
all right. I know,
If you
thank
want to appear, I don't know, but we are live now.
Okay, no problem. Thank you.
You're welcome.
Hello.
Salve, prof.
Hello. Just checking in.
Okay.
Just checking in if
We have
everything's fine.
Luisa here.
Okay. And another person. Ok.
Yes, but I don't know who it is.
Quindi Luisa parla italiano.
No. You're muted, Luisa.
You have to turn on your microphone.
Yes. I
How are
speak
you?
Portuguese.
Ah, all right. Ah. Bene, bene. Okay.
Bene, bene. Sì.
So your session starts now in a couple
Yes,
of minutes.
I think Nadia should be arriving. She's chairing the session.
Okay, so someone, I see another person, and well, probably people will arrive. Okay, tell me if there are problems. I'm just making a little round, checking if all the rooms are fine.
For me, it seems okay.
Yes, I can see you. I can see you and hear you clearly.
Yes, me too.
Okay, good. How many people? How many papers do you have in this
In this
session?
session, there are 2 papers.
2 papers. Okay, and the authors, you know, they are coming, right?
Well, I check it with the other one that should present. It's Mama Bugerara.
Okay. Okay, so if they don't have problems, I think they should be fine.
Yes,
Okay. So have a good session. Goodbye.
Thank you very much.
See you soon.
Thank you
Bye.
very much.
Okay, so we wait another 3 minutes and then.
Yes, no problem for me, because I believe both Nadia and Mama should be on.
Okay, okay. So we wait.
I think I'm going to check.
Okay. Thanks,
You're welcome.
Luisa.
Thank you.
Okay. There is someone here. Hi.
Hi, I'm Nadia.
Ah, hi. I'm Sarah, the GT moderator of the room.
All right, thank you.
Okay. So here we are.
Hello.
Hi. Okay, so if you have technical problems with the presentation, you can ask to me, okay? Okay.
I have to call on the first author.
Yes,
First
what?
author is not on the room.
I didn't hear, I'm sorry.
All right.
The first author?
Is not in the room.
No, I know. We have just Luisa here. Maybe it's arrived.
Let me.
Hi.
Hello.
Oh, it's arrived. Okay. So I close this one. And we are on time. I think that we can go. Okay.
Let me just introduce the authors.
Yes. The stage is yours.
Okay, thank you. Okay, we're here. We'd like to welcome you to We would like to welcome you to the ICCSA 2020, and especially to the Bianca special session.
Mama, you can close your microphone until you have to talk, please.
We have two papers, one on application mapping on 3D NOx using differential evolution, and the other one is about identification of client profile using convolutional neural network. So the first one is going to be presented by Mamar from Algeria, and it's about mapping application on 3D NOx. Mamar, the floor is yours. Okay, you can go ahead.
Can you hear me? Hello?
Yes, yes.
So,
maybe you can make a full screen of the
my name is Boughrar Ma'mar. I want to present to you our work that the title is Application Mapping onto 3D Network on Chip using Differential Evolution. This is the outline. System on chip integrates a complete system into a single chip. The number of integrated components continue to increase to meet the requirement of today's application. The designer of system on chip focus on communication more than computation. Network on chip is the solution to on-chip communication. It's similar to a general network, but with limited research.
Mama?
Yes.
Okay, all right.
The network on chip is an intellectual property that can implement many tasks and execute them as the general purpose processor does. But the EP block is conditional to execute some types of tasks. A network on chip is a set of resources and switches. Resources and switches are connected by links and form tiles. The simple way to connect this tile is to use a topology. Among the most used topology, we have 2D mesh, but 2D mesh does not meet system-on-chip design requirement in terms of area and performance when the number of tiles increase in the same shape. 3D mesh is an effective solution. 3D mesh is implemented by stacking several layers of 2D mesh and providing vertical links for interlayer communication. This chart presents the network on chip design flow. We have three essential steps to optimize: task assignment, EP mapping, and routing. In this work, we take into account two steps, the task assignment and EP mapping. The first step of the problem is EP assignment is to associate the task of the application to EP block from EP repository. The second step is EP mapping. The result of EP assignment is used to map the IP block into the network on chip. To give the best assignment and best mapping, we use some objective. In this work, we use three objectives: area, power, and time. When we say time, we say scheduling. In this work, ASAP scheduling is used. It schedules the task as the earliest possible step.
Mama, the slides are not showing. It's on the first on the network on chip slide. You have to advance the slides.
I was watching normally.
Yeah, I don't have this.
Yes, me too.
I was following. No problem.
No. Okay, all right.
I continue?
Yes, please.
In the AP mapping, we have also three objectives: area and power and time. The problem of AP assignment and AP mapping are NP-hard problem in network-on-chip design. We use one of the optimization algorithms. In our work, we propose to use differential evolution. Differential evolution is an evolutionary algorithm proposed by Price and Stone in 1995. It's considered as one of the most powerful evolutionary algorithms. Differential evolution has 4 steps. The first step is initialization, is to initialize the population and initialize the parameter of the differential evolution. The second step is the mutation is to disrupt the population using a specific strategy. In this work, we use 3 strategies. The first based on the rand, the second is based on the best, and the third is based on the current and best. The third step is crossover or recombination, is improve the diversity of the population. The crossover uses the mutation vector to exchange its component with the target vector to form a trial vector. The last step is selection. The selection is to evaluate the trial vector according to the objective function. If the trial vector is better than the target one, the trial vector will replace the target one. In order to extend the differential evolution algorithm to solve multi-objective optimization, we use the Pareto concept. The algorithm is modified to support the Pareto concept. The solution is a set of not-dominated solutions. To compare our algorithm, we use 2 topology, 2D and 3D mesh. We use a benchmark created by TGFF tools, and also we compare our result with particle swarm optimization algorithm. After several tests, we select this parameter of the algorithm. These are the 5 benchmarks used in the test. The result obtained show that the algorithm is more efficiency in the 3 objectives. First, in the objective of area and 2D. Second, and in the power, and also in the time. he gives a good result compared to the algorithm based on particle swarm optimization. The same algorithm give also better result in 3D mesh in area and also power and time. So we note that the use of differential evolution with best and rand strategy gives better result, and also more especially in using best strategy. In conclusion, the problem of assigning and mapping NP-hard problem in the network-on-chip design, we propose a multi-objective algorithm based on differential evolution to help the designer to select the appropriate AP from IP repository and mapping this IP into network-on-chip physical structure. Two topologies are used in the test, 2D and 3D. The obtained results show that 3D mesh topology perform better than 2D mesh, and also the result obtained show that differential evolution for multi-objective perform better than multi-objective power particle swarm optimization. Best based mutation gives better result than other mutation strategy. For future work, we intend to apply other new evolutionary algorithm or techniques such as BAT algorithm, Wolf algorithm, etc. And also we intend to tackle routing step. Thank you for your attention.
Thank you, Marama, for the presentation. Any questions? I don't know who's the other person that is here. Any question from the floor? No?
Yes, Louise, I have a question.
All right. Go ahead.
Just not to pass without any question. But how long do you think it will take for the routing problem?
I don't hear the question, please. Can you repeat?
Yes. You plan to tackle the routing problem?
Yes.
Yes. Do you have an idea how long it will take to assign it? To work on it? Do you have an idea?
The routing step is used in the assignment when we use mapping step because the mapping step is to send data between IP to another. So the data is a route or choice a route to send data between two IP. In this work, we use a simple routing step, but for the future, we attempt to use evolutionary algorithm to tackle routing step.
All right. Okay. Okay. Thank you.
Thank you. Thank you.
Now we have Louise, we have the floor for your presentation.
Thank you.
Can you share your screen?
Yes, yes, yes. It's stuck in here. I don't know. You are not seeing me, no?
We see you, but not your screen.
Yes, I have a window calling, asking for compartilhar.
For
sharing,
what?
Sharing, but
The sharing button is in the left,
Yes,
at the bottom left.
I chose it, and it came a window asking
Yes.
3
Your
options.
screen, application, or browser kit.
Yes.
And which one do you want to use?
Yeah. Okay. Okay. Now I had to choose the screen.
Okay.
All right. So.
Okay. Now you are sharing.
Can you see by my?
Yes, yes.
Now
we see. Okay. Nadia, I see you talking, but your microphone muted. Okay.
Yes, I see.
Okay.
Okay,
so Luisa, you can go.
Okay, thank you. Nadia, do you want the word?
You can start, Luisa.
Okay, thank you. Well, good afternoon. I am Luisa, and I'm here to present the work entitled Identification of Client Profile using Convolutional Neural Networks. This work is the result of master dissertation developed by Victor Ribeiro de Azevedo, and he was supervised by Professor Nadia Neja and myself. So this talk will follow these steps. We'll make a brief introduction and then talk slightly about the convolutional neural networks and define the main objectives of this work, present methodology adopted, present some results based on which we draw some conclusions and future work. Well, the aim of this work is to address social networks. And in this case, these social networks, they provide large volume of information, such as images and videos, and making it necessary to develop new techniques to extract relevant information from the users themselves. And with segmentation of customers, it's possible to predict users' interests or create advertisements directed to different publics. And one example of this social networks is Instagram, one of the most popular one, with more than 1 billion active users. But we can cite as well Twitter and WhatsApp and Facebook Messenger. It's important to mention that 72% of the users of Instagram say they bought a product they saw in the application, which is very important for commercial interest. Well, deep learning is a subcategory of machine learning where high complexity neural network models are used to recognize patterns. And the recognition of patterns in image and videos can be considered one of the most widely used applications of deep learning. Not only this, but is the main case of interest. And convolutional neural networks are deep learning models, usually used for pattern recognition and classification applications directed to images and videos. In the sense, in the context of CNN, convolutional neural networks, we can say that it consists of an input layer, which receives the images, a series of layers which perform image processing operations with characteristics map, and a last step that contains a classification neural network, complete one, which receives the characteristics map and outputs the result of the classification. This figure is a common one, very used to address the concept of convolutional neural networks. So you have the input image, the feature maps that are constructed along the process due to convolutional operations. And finally, the last step is a fully connected network, which provides the result of the classification. So the objective of this work is to contribute to the field of computational vision and image classification with exploratory and experimental analysis of the performance of CNN. So we are addressing here the performance of the CNN. We are not changing the CNN in terms of its architecture, but using the CNN and try to provide the best performance possible. In order to improve the performance of the CNN, experiments are performed varying the structure of the training algorithms and the initialization of hyperparameters, such as number of epochs and the rate of learning. So this is our main concern in this work. So our methodology. For the development of the training model, a virtual environment is created with the Docker container, which is a standard encapsulated environment that runs applications through virtualization at the operating system level. We use TensorFlow and Keras with the language Python to perform the training. And the model is tested with 5 learning algorithms: stochastic gradient descent, usually addressed as SGD, AdaGrade, RMS-Prop, Adam, and Adamax. So these are 5 learning algorithms that we are experimenting in this CNN, in this work. The performance of each algorithm is analyzed based on accuracy, precision, specificity, recall, and F-measure. Right? About 1,500 images were organized into 5 categories. So we have domestic animals, electronics, games, vehicles, and clothing. The set of images is divided in 8% for training and 20% for testing. The network architecture is defined with 7 layers of 2D convolution. Max pooling function is used with dimension 2x2 and 3x3. And the rectilinear unit is used as activation function, ReLU. And the fully connected final layer is created using the softmax function for classification. Dropout layers are added to the network to control the overfitting problem and the increased error problem in the training. So we have here one set of results based on the training with SGD carried out with 20 epochs. We can see that the curves for training is the red one, and testing for the blue one, have good general relative stability in error decay, reaching 0.45 and 0.436 respectively. So this is a good behavior. And it's possible to visualize the growth of training accuracy and validation accuracy, reaching performance of almost 81% for training and 82% for test. And in here, we can see the increase of the hit rate with the visualization of a stable increase of the metrics: F-measure, precision, and recall. So this set of metrics, increasing these metrics, provides a very good hit rate. And here we are observing the results based on AdaGrade algorithm, carried out in here with 15 epochs and initial learning rate of 0.01. Also, we can see that the error decay along the epochs decrease for both training and testing curves. The growth of training accuracy and validation, reaching performance of 90% for training and 89% for testing, offers better results than SGD. We are just, later on, I will show you a table that will provide all these results comparatively. It's possible to observe also an unstable increase of the metrics F measure, precision, and recall. In spite of being unstable, it's increasing, which shows an increasing hit rate. The training is performed, in this case, using RMS prop with 20 epochs and an initial learning rate of 0.001. Also, we can see error decaying, both for training and for testing. We can see here the growth in accuracy, reaching 92% for training, and validation, 89%. There is an unstable increase of the metrics F measure, precision, and recall. So this increase also reflects an increase in hit rate. Here we have the Adam algorithm running with 50 epochs. It gives a minimum decay error over 0.12 for training and 0.23 for testing, showing good performance of this algorithm. We have here also the growth of accuracy and validation, reach performance of 95%, almost around, for training and 92% for testing. High performance in both steps. It's possible to observe some values in the increase of the metrics, F measure, precision, and recall. But they also provide, this algorithm also provides an increase in hit rate. ADAMAX algorithm runs here with 20 epochs, and we can see also error decaying for training and testing. In this case, we can see also the growth of training accuracy and validation accuracy for both for training and testing. We can observe increase in hit rate, providing a stable result for the metrics F measure, precision, and recall. Okay, so based on this, we can synthesize our results. The worst accuracy for training is 80%, 8.8% for the SGD algorithm, and the highest accuracy is 95.36 for the Adam algorithm. The smallest errors observed for training is 0.12 for the Adam algorithm, as this table can show. So minimum error, Adam, maximum accuracy, Adam as well. The worst accuracy for testing is for testing here, and the other one was for training. For SGD algorithm, and the highest accuracy is of 92% for the Adam algorithm. The smallest error observed for testing is 0.23 for the Adam algorithm, as we can see in this table, right? So minimum error for Adam and maximum accuracy also for Adam. And here is the set of image used in this experiment. So we can see that for animals, for example, we have dog, cat, birds, and these we have high accuracy, indicating that this the set of parameters and the algorithms provide good generalization capacity. Electronics, we have notebooks, TV, cell phones, games. Others have here chair, for example, 66. But this is not compared with the others that we have the object addressed. So as conclusion, we use convolutional neural network as a computational intelligence technique to predict the interest of social network users in certain categories of products using image classification. The comparison of the training algorithms, SGD, ADAGRAD, ADAMAX, RMS-PROC, and ADAM, allows us to verify that ADAM obtains higher accuracy and performance than the others. And as for future work, we intend to vary the image categories in order to obtain classifications with greater generalization capacity. Thank you. Grazie. Obrigada. Are you not sleeping?
Thanks, Luisa. Nadia, you have again the microphone muted.
Okay, thank you, Luisa. Any question? Mama, do you have any question? No? Any chance to put this tool in a real application? Luisa.
I couldn't understand.
Is there any chance to have this tool to be used in a real application?
I believe so. Well, we used in the set of benchmarks that were provided by the platform, but it would be an interesting work to address a real one. Mm-hmm. I believe so, but it requires some more time.
Mm-hmm. I understand. Thank you. Any question? Any further question? No? Thank you. We have only these two papers. They were presented. I hope you took advantage of the presentations. Thank you for the effort to submit the paper and to present it, even though these conditions, we would like to travel to Italy instead of staying at home. But
it will be better.
Nothing, right? It's better than nothing. Okay, thank you very much. Thank you.
Thanks. Bye.
Thank you. Bye-bye.
Bye.
Good luck.
Thanks.
Thank you.